fundamentals. Now with the cantilevers. We will discuss concentrated loads and distributed loads. Welcome back. Now let's go to the cantilevers. A cantilever beam is a beam that has a free end, free of supports, and another end fixed that carries a moment. Our first case has a concentrated shear of value P. The reactions at A are XA, which is 0, YA, and MA. We will start computing MA. Taking moments about A, YA is cancelled. Moment is MA, and only force making a moment is P multiplied by L. So we have the following equation. P multiplied by L rotating about A, and MA rotating in the opposite sense. This gives MA equals P multiplied by L. Taking sigma forces in the y direction equals 0, we have P minus YA equals 0, and therefore YA equals P. Shear force diagram. Starting from the left-hand side, we will head downwards if the force is downwards, and we will head upwards if the force is upwards. And along the beam, the shear is accumulative, means we will add and subtract forces perpendicular to the direction, to the beam in the direction of the shear, as long as we meet them. So, Q at the free end equals minus P. And we encounter no shear forces until we reach A. We meet YA heading upwards. We head upwards by the value P. For the bending moment diagram, we have 0 moment at the free end, and at the fixation, we have the moment PL. So we simply plot it, and that's our bending moment diagram. Now, a cantilever beam with distributed load W tons per meter run. First, we compute our reactions. We have our virtual resultant WL instead of W ton per meter run. We have an XA reaction equals 0 and YA, MA, 2 reactions needed to be computed. Sigma forces in the direction of Y equals 0 makes YA equals WL. To be in equilibrium with this red resultant. Our moment is simply this red WL multiplied by the arm of the force till it reaches A, L over 2, giving a moment at the fixation equals WL squared over 2, and with a tail upwards. Shear forces diagram. Again, take the section at X here, at a distance X from the free end of the beam. Get a section, and the shear force will be minus WX, which means the force is heading downwards. And please note that the positive shear notations is computing from the left hand side. The shear heads upwards, so it has a negative sign here because it is heading downwards. Simply substitute for X by x equals 0, expressing the free end of the beam and having shear equals 0. Then substitute x equals L, which means we reached the point A, and therefore the shear there is minus WL. Simply plot this linear equation, plot an inclined line that starts with 0 and ends at A with WL. Here you are. For the moments, the bending moment diagram, again you have at section S the equation of the moment equal to Wx, the virtual resultant, multiplied by the arm of this force, which is x over 2, making Wx squared over 2. Again, please recall the sign convention of the bending moment. Here we have our elemental beam. The moments with the tail downwards, lower fibers are under tension, is the positive moment. If you have the opposite, the tail of the moments upwards, then you have a negative bending moment, which is our case here. Note that the tail of the load is the same as the tail of the bending moment because the load is the cause of the moment. So now we have a parabolic equation. At x equals L, we have a moment of minus WL squared over 2, which is really the value of the reaction MA. Just plot it and have this dashed line to drop a parabola of WL squared over 8, which is really the same drop of the simple beam discussed previously. If you want to make sure of this piece of information, you can just substitute for x in the parabolic equation by L over 2. Then you will get this value here. Subtracting it from the value WL squared over 4, which is half this value, you get WL squared over 8.